Hello everyone, welcome to ashatech.com. In this lecture, we are going to discuss shear stress. Let us consider a block or portion of material as shown in A. This is A and is being subjected to two equal opposite forces Q that are acting tangentially to the material. It is going to be observed that shear stresses tau, like for example in B, are going to set up and will shear the material. So this material is going to fail under shear stress. So the material in A is subjected to a set of equal and opposite forces Q. Such a system could be realized in a brake block when contacted with a wheel. For example, let us look at a bicycle braking system. If this is a wheel, for example, and it is rotating in this direction, then there is a tangential force on the wheel. If this is the brake block, if you apply brakes and the wheel is rotating in this way, this is going to set up a force. A force is going to be built up on the block and it is going to oppose the motion of the wheel. So the force that will act tangentially on the material of the block is going to act opposite. But this force, if this is Q, it will equal to this Q that is meant to be applied to stop the wheel from moving. There is then a tendency for one layer of the material to slide over another to produce the form of failure shown in B. So this material of the block, if we observed it properly, if it is to fail, then it can fail by shearing. You can have some layer being removed from the other layer, and therefore these two layers are going to move in opposite directions, tangentially to each other. Therefore, if this failure is restricted in one way or the other, then a shear stress is going to be set up. So if you restrict the failure of that block, then the shear stress is set up and this is given as tau. This is tau. Therefore, this one is showing the shear force and resisting shear stress system, showing typical form of failure by relative sliding of planes. Now, having had that introduction, we can define shear stress. Therefore, shear stress is defined as shear load. This is shear stress tau equal to shear load divided by area resisting shear. So this is shear stress tau is equal to shear load, and according to the above system, it is Q divided by area resisting shear, and this is A. It will be observed that therefore that tau equal to Q out of A, and this can be in kilonewton per square meter. It can also be in meganewton per square meter, etc. 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 This shear stress, we must observe that it is always going to be tangential to the area on which it acts. However, direct stresses are always acting normal to the area on which they act. Now, if this is a shear stress system, it is acting tangential. It is acting tangentially on the area onto which it is acting. This is the area where it is acting. Whereas, if it is this is the shear stress tau, if it is the normal stress system, then you could have something of the sort. If we consider tensile stress system, then it will be of this, whereby this is the area, this is the area. Now, this is the normal stress system. So you can note the difference between shear stress and normal stress. The shear stress is acting tangentially to the area on which where it is being subjected, whereas in a normal stress or direct stress are always acting. Those normal stresses are always acting normal to the area on which they are applied. Okay, and all these are on load over area. That is tau. Even this sigma normal stress is equal to load over area. So this one is a shear load, this one is the load applied normal to the area, and these are the areas onto which those forces creating the stresses are being applied. Let's go ahead and look at shear strain. If one considers the block, for example, that block in A having been acted on by the shear loads or shear stress, it will produce figure C, like as you see it here. If this was a bicycle brake block, it is clear that the rectangular shape of the block will not be retained as the brake is applied and shear forces introduced. The block will in fact change shape, or it will undergo strain into the form shown in the figure below. For example, you look at this, we are saying if those forces continued acting, what will happen later on if the shear stresses are built up, then the rectangular shape will actually be lost, and this is what is going to happen. This is going to be the stress, this is going to be the stress, and it will undergo an angular strain, which will be gamma. So this is the shear stress, this is gamma, which indicates the shear strain the object has undergone. So shear strain is therefore the angle of deformation when shear stress is applied on an object. This shear strain is therefore measured in radians. Shear strain is angular deformation. And therefore it will be given by the angle which the material has been deformed. The angle by which the material has been deformed will give you the shear strain, and therefore this will equal to gamma, as we have already seen from above. Let us also talk about another important concept in shear stress, and this is none other than modulus of rigidity. Now we shall also note that for materials within the elastic range or in the proportionality limit, it has been found experimentally that shear stress is proportional to shear strain. In other words, experiments have been made and it has been concluded that the shear stress is directly proportional to the shear strain. So that means tau is equal to, if we introduce a constant c times gamma, it means tau out of gamma is equal to that constant c. It therefore means that this constant c is the constant of proportionality, and it is what is regarded as the modulus of rigidity. Therefore c is the modulus of rigidity. So we have said this is tau out of gamma is equal to c, and that means if this is in radians and this is in, for example, maybe kilonewton or meganewton per square meter, it means this modulus of rigidity is also going to take the units of stress, of shear stress, which may be meganewton per square meter, but it is always found out that materials have a value which is given as giganewton per square meter. So this constant c is termed as modulus of rigidity, or what we can call shear modulus, and is directly comparable to the modulus of elasticity used in direct stress application. So it is actually also a property of materials. Now the different values of modulus of rigidity have been given for different materials, and we can see that the steel has about 80 to 100 giganewton per square meter. Rough iron has got 80 to 90, up to timber, which has got about 10 giganewton per square meter.